So we want to start taking some time to think about what it means to get closer and closer. And I mean, intuitively, we know what it means. It's like we're zooming in. Like if you have a phone and you're doing your pinch zoom and you keep zooming in and zooming in and zooming in. Or if you're watching one of those fancy detective shows where they say enhance, 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 enhance. And, well, what does it really mean? And how do we do it? What's the process? So that's our goal for today. And spoiler alerts, it's something that we call limits. And so if you've ever heard the word limits, that's what we're getting into today. So let's start by looking at motivation. So if you recall, we were thinking about this idea where we were after a tangent line, this line right here, which is a tangent line to a particular curve. And our idea, and it's a great idea, we said, hey, tangent lines are hard because you only know one point, because the word tangent means we touch at one point. Secant lines are easy because at secant lines, for example, this dotted line, we touch at 2 points. And 2 points is enough to make a line. So the idea was we start with the secant line, which is maybe a bad approximation. Then we make a closer, in some sense, secant line by moving the point, that extra point of tangency, nearer to the one we want. And then we repeat, repeat, repeat. And so the idea is, as we get that point closer and closer, in other words, as B gets close to A, then what we do is we're getting a better approximation to our tangent line, and that's going to be what we want. All right. Now, this poses a question. Well, we know we want B to get closer to A. Why not just put in B equals A? Okay, I'm going to restart. I'm not very happy with the current setup because I forgot to turn on the light. Okay. All right, so Steve, we're starting at 4:10. I only got 25 minutes until this stops. And I don't want to do 25 minutes of talking. All right, time for the big idea. And what is it? Well, what do we mean when we talk about getting closer and closer and closer? What is that? And how do we deal with it? Well, you may have heard it before. It's called limits. But why are we studying this? Why do we want to get closer and closer? So let's take a second and recall our motivation. So, start with the picture. So I have a curve here, and I'm after understanding the rate of change of the curve, which is somehow like a slope. So the way we do it is we say, look at this tangent line. The slope of the tangent line, that's what we call the instantaneous rate of change. So I want to know that slope of that tangent line. So how do I find it? Well, the problem with the tangent line is it touches at 1 point. That's not enough to make a slope. A secant line, on the other hand, goes through 2 points. And 2 points is enough to make a slope. So, our great aha. What we do is we say, well, I'm going to start with the secant line. So, for example, let's say between this point A and this point B. And now, that is an approximation of sorts to our tangent line. Not a very good one right now. But that's because somehow A and B are far apart. So what do? We move our B closer. And it's a better approximation. What do? To get a better one, move it even closer. And we're going to keep doing this. Closer and closer and closer. As we repeat that process, we're going to get better and better approximations. And so, what are we looking at? Well, we're looking at this slope of the secant line, f of b minus f of a over b minus a. That's our desired slope of our secant line. And we're asking what happens as our b gets closer and closer to a. Well, why not just put in b equals a? That would be the best. Like, that's the closest you can get. You can't get any closer than being right there. Well, let's see what happens. F of a minus f of a, 0. A minus A, 0. 0 over 0. Now, what happened? We got 0 over 0. And one of the things that we often remember from our algebra teachers, they tell us, don't divide by 0. You can't do it. It's a terrible thing. Why is it a terrible thing? It's useful to understand that. So let's think about it. Why is division by 0 bad? Well, one of the things we can say is that if you take A divided by B, when we say that that equals a value C, so A over B equals C, really what we mean is that A is the result of multiplying B and C together. That's a pretty reasonable idea. So it's sort of a way of connecting multiplication and division. So now let's divide by 0. So in other words, I'm going to have something over 0. So A over 0 equals C. Well, that means A equals 0 times C, which is 0. Now, there's two possible outcomes. One outcome is if A is not 0. Now, why is that bad? Well, because this says A has to equal 0. So A can't both not be 0 and be 0 at the same time. It's an impossible situation. You have to pick a side. All right. So that's why division by 0 is bad if the numerator is not 0. But wait a second. What if the numerator is 0? Then I have 0 equals 0, and life is good, right? Except for one thing. What's the right choice for C? You see, when we say what's the right choice for C, what C makes it true? And the answer is that any C would work. So that there's not one particular possible answer, there's many possible answers. And so that tells us, hey, we don't know what it is. It's an ambiguous value. Now, ambiguous is a very long word. There's another word that you're going to hear from time to time. It's called indeterminate. And what does it mean? Well, it means we don't know. Well, that seems like an easier way to say that. So it's some value that we don't know. So whenever we see 0 over 0, that's an example of something which is indeterminate. We don't know what the value is. So what do we do? Now, let's talk about what we don't do. 0 over 0 is not going to automatically be 1. There will from time to time be cases where 0 over 0 is in fact equal to 1. But it's not, like we can cancel the zeros. That's not how it works here. You got to be a little bit more careful. So what does 0 over 0 mean? Well, the real answer is when you see 0 over 0, from now until the end, what is it going to mean? It's going to mean more work. Why do I say that? Well, because we don't know what it is. But maybe we can figure out what it should be. And that's the great challenge. So there's where limits come in. Limits ask the question, what should happen? You see, I don't know what 0 over 0 is, but what should it be? See, if you went back to our picture, where did our picture go? Oh, it's underneath. Okay, if we went back to this picture here, you can say, look, there is some slope. This line is a line. And so the real question is, what should that slope be? That's what we're doing. That's what we're trying to figure out. All right, so when we talk about limits, here's what we mean. We say that the limit as x approaches a of f of x is L. That's how you read this statement. Limit as x goes to a of f of x is or equals L. Means as this x is approaching a, then this f of x is getting close to L. So as x gets close to a, the output gets close to L. Okay. Now how do we figure it out? Well, what we do is we say, well, let's look at the function around us and see if we can't figure out what it should be. Oftentimes what's happening is there's a hole that you have a sort of a missing gap. So for example, that f of b minus a, f of b minus f of a over b minus a, there's a hole when b equals a. That's a missing point. But maybe when we look on either side, the function actually is pretty good, and therefore we have something we can work with. So we want to start building up our intuition of limits, and we're going to spend a couple times talking about limits. So don't worry, if you don't get it now, you'll have many more chances to not get it later. No, come on, we're going to get it. Remember the intuition. As x gets close to a, f of x gets close to L. And if you remember that, it's not so hard to figure out some basic properties. So here's some list of basic properties. And let's see if we can convince ourselves of some of these properties. So let's start with, say, this one. This says, as x gets close to a, this c. Now notice that there's no x involved. So c is a number. So the value c, what happens to it? Well, if I'm a constant, it doesn't matter what x does. I'm always that same constant. So as x gets close to a, that constant always stays a constant, so the result is c. All right, that's pretty convincing. Let's think about this one. So this is the limit as x goes to a of x. So we're trying to figure out, as x gets close to a, what does x get close to? And the answer is a. Okay, good. These we can believe. So those are some basics. But of course, we don't want to do it individually, so we want to start saying, here's some building blocks. Now let's look for ways to put things together. So suppose we happen to know some limits. As x gets close to a of some function f of x, I got L. And as x gets close to a of g of x, I got M. Then what I can do is I can combine them together. So this is a constant c times f of x plus a constant d times g of x. And so what's happening? Well, this is getting close to L. This is getting close to M. So the whole expression is getting close to c times L plus d times M. That seems very reasonable because, well, it's true. Now, by the way, this has a very fancy term for it. And what this says is that this is a linear. In other words, it respects addition, and you can pull out constants. Now, while I'm saying that, there's this little warning down here I want to draw your attention to. It says, hey, be careful. It's possible for the limit of two things put together to exist, even though the individual limits fail to exist. So just because I have an addition doesn't mean I can break my limit up into two parts. I have to make sure that each one of the parts also has its own limit. It's possible that when they combine, somehow the badness, what's causing it not to have a limit, goes away. All right, so that is addition. We should think of this as really addition and then being able to pull out scalars. So scalars is a fancy way to say a number, a constant. We can also say that if I have two functions multiplying together, so f is getting close to L, g is getting close to M, so I have something close to L times something close to M, well, that should be getting close to L times M. And it does. Aha, good. Now, what about division? Well, the answer is it does exactly what you think, unless, of course, the denominator is 0. When the denominator is 0, all bets are off because we don't know. And the really interesting case, of course, is 0 over 0. And when you see 0 over 0, more work. Now this last one, it says, suppose I have a function to a power. And for right now, we'll think of the power could be a whole number, or maybe L, here the limit could be a positive number. And so let's suppose we are in that situation. Then what I can do is I can say, look, the inside is getting close to L. So I have something close to L raised to the qth power. So the whole expression is getting close to L raised to the qth power. Now, if all of these things sound obvious, good. That's what we want. Limits should behave in a really proper way. In other words, they shouldn't do anything surprising. If it's a reasonable thing we expect to be true, it's often true. Now, that's our intuition. There are some technical things that we get into, but for now, that works well enough. So what can we do with this? Well, we'd like to come up with some functions which we understand and are easy for us to work with. And what do we have? Well, I can work with things that look like a constant. I can work with things that look like an x. I can add. I can multiply. And if you start thinking about, well, what kind of things can you form from an x, constants, addition, and multiplication? The answer is you can come up with a really nice set of functions, and they are called the polynomials. So what we have is that polynomials are nice. So what do we mean by they're nice? So suppose I have a polynomial. Now what's a polynomial? It's a combination of powers of x. So cn x to the n plus c1 times x plus c0. So again, we're adding and multiplying constants and variables x. So what we can do is we can now apply our rule. For instance, if I want to know what the limit here of f of x is, okay, well that's the limit of the polynomial. Now, do you see how we have all these additions and all these constants? We can use the fact that we're linear, which means we can break up over addition and break up over constants as long as the limit exists, and we'll get to that in a second. So that's the first part. So we're taking this limit and breaking it into lots of individual limits. Now, the limit of x to a power, see this power, I can move it to the outside. So to the nth power, to the 1th power. Well, here it's really to the 0th power, but that's all right. And now I say, okay, the inside, that's an easy limit. I know what happens as x gets close to a. X gets close to a. So I get cn a to the n plus c1 a and c0 times 1 c0, which is f of a. Now, why do we say this is nice? What this tells us is that if you have a polynomial, what should happen is what does happen. No surprises. And that's the best thing, is when there are no surprises. We're going to talk more about functions which have this property, and that's going to be another day. So we call these functions continuous. So continuous functions are ones where what should happen and what does happen are the same thing. But we'll get into more detail about continuous functions later on. By the way, related to polynomial functions are another class of functions called the rational functions. Now, the rational functions, why do we call them rational? Well, look at the word, ratio. So it means we're dividing. So when we talk about a rational function, it's two things being divided, and in particular, what we mean is a polynomial over a polynomial. So we have two polynomials on top of each other. So what we can say is, look, as long as the denominator is not 0, well, if the denominator is 0, okay, got to restart. But if the denominator is not 0, then again, rational functions are nice because the top is nice and the bottom is nice. Good. So now we have some class of functions which are easy for us to work with. We're going to keep expanding these, and we're going to add more and more understanding to limits. Now, how do we actually go about solving limits? So, the answer is there's some basic strategies. So when the time we really need to work hard is when we have 0 over 0. So we have to think of how do we handle 0 over 0. The underlying idea is if we have 0 over 0, there's something causing a 0 upstairs, and there's something causing a 0 downstairs. So what we should do is think about what's a way we can cancel those zeros. So in other words, find something from the top and something from the bottom which we can cancel out. That's our sort of our general approach. So how do we do it? Well, the answer is use your tools. And what are our tools? Well, if we're dealing with polynomials, when you have a 0 in a polynomial, that means you have a root of your polynomial. So what do we do? Well, we take our polynomial, we rewrite it in a nice way, expand it out. Then we factor it. Because we have at 0, we have a root, so we know a little bit about how it factors. And oftentimes just a little bit is enough to get us started. There's another tool we have, which is called multiplying by the conjugate. Now, conjugate is a fancy way of saying multiply by changing the sign. So a plus b, a minus b. So the conjugate says I'm flipping the sign. So positive to negative. Now, why do we like that? Well, the reason we like that is I can take something that maybe looks like a minus b, and I can make it something that looks like a squared minus b squared. Well, why is that helpful? Well, one of the things that can happen is one of my terms might involve a square root. How can I get rid of a square root? Well, I could square things. So how do I make it into a square? Multiply by the conjugate. So this is a way to help us to get rid of square roots. And it's a really nice common tool. So oftentimes if you see square roots involved, think conjugate. Really what's going on with conjugate is to say, would it be helpful if you squared the terms? And if the answer is yes, then life is good. Now, be careful. Follow your rules of algebra. We want to make sure we follow our rules and don't make silly mistakes, because silly mistakes make us feel silly. We don't want that. So, what's an important thing to keep in mind? When we say multiply by the conjugate, we often mean that there's sort of a top and a bottom, right? Because you have 0 over 0. You have to multiply by both the top and the bottom. Now, if you multiply both top and bottom, you're multiplying by 1. And you can always multiply by 1. You're okay. So that's fine. But if you only multiply the top, no good. No good. Now, another note about conjugates. When you multiply top and bottom, we don't value them equally. So, in other words, one of the things you have to decide is where do you expand and where do you not expand. The rule of thumb is as follows. Expand when it helps give you information. And if it's not helpful, don't do it. Don't do it. Because we want to make sure that we do the right amount of work, but we don't want to do too much extra work, and especially we don't want to increase our chance of errors. We want to avoid those. So be careful. We're going to go through some examples in our practice so you can see all these things happening. The last thing that you might look for is if you see trigonometry involved, then you might say, well, let me try to pull out some trig identities. And the most important trig identity in this case is sine squared plus cosine squared equals 1. Now notice you have squares. Well, that can be a really useful thing for us to use conjugates for. So what's really going on? When we're trying to find limits, our real goal is let's try to rewrite in such a way that we can get some nice cancellation and get it to something that we can work with. So that's our goal. Cancel the zeros, cancel the zeros. And of course, let's be careful with our algebra. This starts to be the point when it really, really matters that we're careful with our algebra and make sure we understand things. And a lot of people start doing crazy stuff. So they'll say things such as, take 16 over 64, and they say, hey, wait, okay, well, let's just simplify it. That's not so bad, right? Because what do? They both have the 6's, right? And so we end up with 1/4, which is, actually is 1/4. Okay, that's a bad example, All right, here's a better example. Look, 19 over 95, right? What do? Well, you can cancel the 9's, right? And that's 1/5. Wait, that is 1/5. All right. Okay, so, but on a serious note, one of the things that we often see is we see things such as this. X plus 1 over x plus 5. And people will say, well, that's like x over x and 1 over 5. No, definitely not. Definitely not. There's all sorts of crazy things that happen. So be careful. This, by the way, is just a fun little coincidence. And you always have to be careful. Yes, there are some fun, cute little things that happen, but that doesn't mean they always happen. You want to make sure that you know your algebra, know what does work, and know what doesn't work, because we want to make sure we keep getting the right answers. All right, time for some practice.